The next topic is viscosity. Viscosity means the property of the liquid by which it resists the flow. So always when the liquid or the fluid is in motion, among its different layers there is a resistive force like the force of friction. So which oppose the relative motion of each layers. That resistive force we call as viscous force, and the phenomenon by which a liquid or a fluid exert viscous force is called as viscosity. So the tangential force that tends to destroy the relative motion among different layers of the liquid is called as viscous force. And as I said, it is analogous to friction when a solid substance when it moves over a surface. We can assume the flow of liquid to be in the form of flow of or the movement of different layers. So the viscous force between the layers, it depends on the area of the layers, relative velocity between the layers and the distance between them. And this type of motion which we consider in the form of layers, we call it as laminar flow. So in laminar flow, we can assume the liquid flow to be in form of different layers, and the viscous force acting it is directly proportional to, or it depends on area of the layers, relative velocity between the layers and the distance between them. We can say that for any layer of the liquid, suppose we are considering an innermost layer. So the upper layer and lower layer, it is in direct contact with that particular layer. So we can say that for that layer, its upper layer pulls it forward while the lower layer pulls it backward. This is actually what is happening when we assume the liquid motion, the flow of liquid to be in form of different layers. For a layer which is well inside the flow, means the liquid which is in flow, for that particular layer, we can assume its upper layer and lower layer. So the upper layer which is in direct contact with this particular layer, it pulls it forward, whereas the lower layer, it pulls it backward. And this pulling and pushing only results in that viscous force. And different layers of liquid will be having different velocities. When we consider a liquid flowing in an open space, not like a tube or pipe, the topmost layer will be having highest velocity, and the layer which is in contact with the floor, that layer will be having lowest velocity, or the speed will be lowest one for the layer which is in direct contact with the ground, and the topmost layer will have the highest velocity. When we consider the fluid which is flowing in a pipe or a tube, the velocity of the liquid layer along the axis, that means in the middle of the tube, okay, along the axis of the tube, that layer will be having maximum speed, and the speed decreases gradually outwards, and finally that means the layer which is in contact with the surface of the tube, that layer, it is supposed to have almost zero velocity. So that is the case. So innermost layer, that means the middle one, will be having the highest velocity. So this diagram shows the streamlines of a liquid flow through a tube. So that length of the streamline shows that velocity or the speed. So speed is maximum in the middle. Now we will discuss Newton's viscous formula. For that we consider a layer of liquid which is between two glass plates. Lower glass plate is kept fixed, and the upper glass plate is just pushed tangentially. So we can say that it moves with a velocity v, and the liquid layers, it suffer a shearing strain. So in the previous chapter when we discussed strain, one type of strain we did not discuss, that is shearing strain. It was deleted from the syllabus. On account of that we did not discuss. So shearing strain is the strain which denotes the change in shape. So actually when we look here, you can see that the liquid column which was rectangular in shape between the two glass plates, on the application of that tangential force, it takes the form of parallelogram. That cross section, you can see that liquid column, now it has changed to the shape of parallelogram. So there is a change in shape. The corresponding strain we call as shearing strain, and that shearing strain is actually here. Here you can see the side which has undergone that change, that slanting, one straight side, no, AB has now taken the form AE. So the side which has undergone change is that side of length L, and it has actually displaced through a distance delta x. You can see delta x here, this is delta x. Okay, so it has been displaced through that much distance. So shearing strain is defined as that displacement by that length L, that means delta x by L. So shearing strain here, it is delta x by L. So according to Sir Isaac Newton, that stress, that shearing stress or that tangential stress is directly proportional to strain rate. Strain rate here, it means rate at which the strain is changing. So we can write stress is proportional to strain by time, where stress is F by A. So our equation, it becomes F by A proportional to delta x by L divided by delta T, where delta T is the time interval for which the force is acting. Or we can write F by A proportional to V delta T by L divided by delta T, because we substituted for delta x is V delta T, velocity into time. So delta T will get cancelled, and we have our expression F by A is proportional to V by L, or F by A equal to a constant of proportionality eta into V by L. Here the constant of proportionality eta is called as coefficient of viscosity. So we can write the viscous force F is equal to eta A V by L. This formula is called as Newton's viscous formula. So in this equation, F gives the viscous force, eta is a constant for a particular liquid called coefficient of viscosity. Now, the new physical quantity coefficient of viscosity can be defined as the ratio of shearing stress to the strain rate. Take care, it is not stress to strain ratio, it is the ratio of stress to strain rate, rate at which the strain is changing. And we have from the Newton's formula of viscosity, we have eta equal to FL by VA. And SI unit of viscosity is poisson, written as PL. Capital letter P, small letter L stands for poisson. And 1 poisson is same as 1 Pascal second, or it is the same as Newton second per meter square. And it has got the dimensional formula ml raised to minus 1 t raised to minus 1. And as I said, viscosity, coefficient of viscosity will be different for different liquids. Generally, thin liquids like water, alcohol, etc. are less viscous than thick liquids like coal tar, blood, glycerin, etc. And the viscosity of liquids decreases with temperature, while it increases in the case of gases. So in the case of liquids, when the temperature increases, viscosity decreases. So here we have a table showing the coefficient of viscosity for different liquids at different temperatures. Blood at 37 degrees Celsius, see its viscosity, it is 2.7 millipoisson. So like that, for different liquids we have the viscosity. Honey is somewhat viscous, it is having 200 millipoisson. Glycerin 830, like that highly viscous liquids we have look at water, water is having only 1 millipoisule viscosity. That means coefficient of viscosity is that much less. So that is the case with the coefficient of viscosity. Now, Stokes' law. Consider a body flowing or falling through a fluid. That means you can assume an object which is falling through a liquid. For example, you are putting a stone in water. So actually, when the stone goes down, it drags a layer of fluid in contact with it. And this body will experience a retarding force. It is due to the viscosity, viscosity of the liquid. So if the object is falling through a highly viscous liquid, it experiences more retarding force because it experiences that much force upward. So its motion gets retarded. Actually, in the case of falling of raindrop, swinging of a pendulum bob, everywhere where air is there, no, actually this viscous effect is there, but this air is less viscous, because of that much we may not experience it. Okay, and this viscous force acting on a body which is moving through a fluid is found to be proportional to the velocity of the object, and of course it is acting in a direction opposite to the direction of motion. So if a stone is falling down through a liquid, on the stone the viscous force is acting upwards. Okay, falling raindrop, viscous force due to air, that is also acting upward direction. So always it is acting in a direction opposite to the direction of motion, and it is proportional to the velocity. So as the velocity increases, the viscous force also increases. So here we are discussing the viscous force acting on a solid which is moving through a fluid. Now, according to Stokes' law, this viscous drag force which is acting on a solid which is falling through a fluid is F is equal to 6 pi eta AV. So this formula we called Stokes formula. F is equal to 6 pi eta AV, where eta is the coefficient of viscosity of the liquid, A is the radius of the spherical body, and V is the speed with which it is moving. So we have the viscous force as 6 pi eta AV. Now, if we consider such a body, so we consider a spherical body, you can assume a spherical metallic sphere which is falling through a liquid, say kerosene oil, not kerosene oil, coconut oil we will consider. Through coconut oil it is falling. So, the forces acting on that spherical body, there are many forces acting on that spherical body. Which all forces are acting on the spherical body? First of all, its weight is acting downwards. That is mg, that is the gravitational force, it is acting downward. And upward forces are acting. One is viscous force, which we discussed just now, and the other is the buoyant force, which you have studied in 9th standard. So there are three forces acting on a body which is falling through a fluid. The three forces are weight acting downward direction, and viscous force and buoyant force acting in the upward direction. So which force is more, in that direction the body will be moving. So that body which is flowing through that liquid, first it will get accelerated because of the weight acting downward. But we said viscous force, it is directly proportional to speed. So as its speed increases, its viscous force also will be increasing. That means upward force increases. So slowly the gravitational force decreases, and at one particular point the net force acting on the object, it becomes zero. If the net force becomes zero, it is not having any acceleration, and thereafter the body will fall down itself with constant speed. Till that point it was under accelerated motion because gravitational force is acting downward. Because of that it was in accelerated motion. But when the net force becomes zero, how the net force became 0 because the viscous force is increasing, because as it comes down because of gravitation its speed is increasing, and this according to Stokes' formula the viscous force is directly proportional to this velocity. So as it comes down its viscous force, the viscous force acting on the body increases. So naturally gravitational force decreases, and finally a point is reached where the net force acting on the object it becomes 0. And thereafter the body will be moving with constant velocity, and the constant velocity is called as terminal velocity. So what we discussed now is the case with a spherical metallic body or metallic sphere which is falling through a liquid, and it is applicable for a falling raindrop also. So when a raindrop falls from a huge height, after falling through some distances, when it approaches the surface of earth, its speed will become constant because of this effect, and it falls with constant velocity, and that constant velocity is called as terminal velocity. So that phenomenon is represented here in the graph. So time is taken along x-axis, velocity along y-axis. So as the time goes, the speed is increasing, and thereafter the speed attains a constant value, and that constant value of speed is called as terminal velocity. Now we will obtain an expression for terminal velocity. So we consider the situation when the body attains terminal velocity. So when the body attains terminal velocity, we said net force is equal to 0. Net force equal to 0 means total downward force is equal to total upward force. In the downward direction only gravitational force is acting, and in the upward direction buoyant force and viscous forces are there. So we can write it in the form of an equation. So we have Fg equal to Fb plus Fv. That means gravitational force is equal to the sum of buoyant force and viscous force. Now we need to write the expressions for gravitational force, this buoyant force and viscous force. You know, viscous force, our expression is 6 pi eta AV. Here we are considering the situation when V is equal to Vt, where Vt is the terminal velocity. So we have 6 pi eta AVt plus buoyant force. You know, buoyant force, it is equal to the weight of the liquid displaced. So weight of the liquid displaced means volume of the object into density of the liquid. So we have 4 by 3 pi a cube. That is what the volume of the object. That much volume of the liquid is displaced. So that into density of the liquid, that is sigma. So sigma is the density of the liquid, and g, in order to make it weight, mass into acceleration due to gravity only weight, no. So we have mass into g, that m, it is 4 by 3 pi a cube sigma, where m we have used the notion that density into volume. Volume is 4 by 3 pi a cube, that into sigma. So that is equal to, here we have gravitational force. Gravitational force is mg. That mg means mass of the spherical body into acceleration due to gravity. We assume the density of the spherical body or metallic body which we considered to be rho. So its volume we already said it is 4 by 3 pi a cube. Volume into its density, that is its mass. That into g will give its weight, which is the gravitational force. So that way we get the equation 6 pi eta AVt plus 4 by 3 pi a cube sigma g equal to 4 by 3 pi a cube rho g. Now we need to rearrange this equation and obtain the expression for terminal velocity, that is Vt. So we have 6 pi eta AVt is equal to 4 by 3 pi a cube g into rho minus sigma. By taking this term to this side, we will get like this. Okay, now we need to write it for what? Vt. So we have Vt is equal to, so by taking the pi will get cancelled, one a also will get cancelled. So here we have a square, and we have 6 here. So when we take 6 to this side, 1 2 will get cancelled and 1 3 will be there. So it becomes 2 by 9. And eta also will be there in the denominator. So 2 by 9 eta into a square g into rho minus sigma. That will be the expression for Vt. So we have the expression for terminal velocity as 2a square by 9 eta into rho minus sigma into g, where a is the radius of the substance, or in the case of raindrop, it is the radius of the raindrop. Sigma is the density of the fluid through which it is falling, and rho is the density of the solid substance. So if we are considering raindrop, that rho is the density of the raindrop. So we can say terminal velocity depends on square of radius of the sphere, and it is inversely proportional to the viscosity, coefficient of viscosity of the medium. So if rho is less than sigma, Vt becomes negative. That means the body will go up. This is the reason why air bubble rises in the liquid and clouds in the sky moves upwards. It is because of that difference in what? Density. So that Vt becomes negative and it moves upward. Now we have one example 1010. The terminal velocity of a copper ball of radius 2 mm falling through a tank of oil at 20 degrees Celsius is 6.5 centimeter per second. Compute the viscosity of the oil at 20 degrees Celsius. Density of the oil is 1.5 into 10 cube kilogram per meter cube, and density of copper is 8.9 into 10 cube kilogram per meter cube. So we have terminal velocity is given and we are asked to find coefficient of viscosity. So first of all, terminal velocity Vt is 6.5 centimeter per second. So we have to convert it into meter per second. So 6.5 into 10 raised to minus 2. And radius it is 2 millimeter. So A is equal to 2 into 10 raised to minus 3 meter. And density of the oil, that is sigma, 1.5 into 10 raised to 3 kilogram per meter cube, and rho is 8.9 into 10 cube. Now what we need to do is just use that equation for Vt, rearrange it to get eta, then substitute. So the answer is 0.99 poiseuille. With that we conclude today's lesson. Thank you.